FormalAnalyticGeo, a neural-symbolic based framework for multimodal analytic geometry problem generation.
You know what's really wild? Most big breakthroughs in math reasoning with AI have been about shapes we can draw on a flat surface. But nobody has figured out how to teach machines to reason about the kind of curves and equations that actually appear in advanced algebra.
Exactly. And here's the interesting part. When we try to build datasets for these problems, most researchers just reuse old geometry tests that were never designed for AI.
That sounds like trying to teach a robot to cook using only recipe cards from the 1800s.
Right. So they ended up creating a whole new dataset called AnalyticGeo 7K, over 7,000 brand new problems where every curve has to match its math exactly.
And how do you even check if their answers are right?
That's the genius part. They built an SDF Engine that doesn't just guess, it actually verifies each step, like a teacher grading homework, but for computers.
So it's not magic, it's math with a side of computer vision.
Precisely. And they didn't stop there. They made sure every problem had both the question in words and a diagram that could be measured pixel by pixel to see if you're correct.
Sounds like they built a super precise puzzle where each piece has to fit perfectly, or else the whole thing falls apart.
And here's what's really cool. When they tested 8 top models on this new dataset, some of them actually improved by almost 20%, just because they had access to these verified examples.
So it's not about smarter robots, it's about giving them better maps for the math terrain they're exploring.
And that map is only as good as how accurately you can draw the curves and check if their answers land where they should.
So we've got this big pool of verified problems, right? Almost 7,000 of them passed all the quality checks.
And each one takes about 5 minutes to generate automatically through Gemini 3.1 Pro Preview via an 8PI.
That means they can keep producing problems without needing human labelers for every single case.
Right. And that scalability is key. Just run more cycles whenever you need more data.
Cool. So what does the dataset look like when broken down by curve and goal types?
The 7,043 problems are spread across 4 curve categories and 5 goal categories. Each curve type makes up between 18 to 32% of the total set, giving us a nice distribution balance.
And which goals appear most often?
Area and chord length dominate as the most frequent objectives. Then we also see distance, angle, and perimeter, adding extra geometric variety.
Interesting spread. What about visual examples? Do they show anything concrete?
Absolutely. Figure 3 highlights 3 representative problems complete with Meiberger answers and analytical solutions, so you can see exactly how they work in practice.
That helps visualize the output. And what about that table comparing problem counts across curve and goal types?
It's essentially a heat map showing where most of the workload lies, highlighting which combinations are common and which might need extra attention or examples.
So it's like spotting bottlenecks in the dataset before diving deeper.
And when we talk quality analysis, think of it as tasting ingredients to ensure flavor consistency.
Got it. So they have these 3 quality gates checking different stages?
Yes. The first gate catches most issues right away with a 99.1% success rate. Think of it like an initial safety net.
And the second and third gates handle more complex checks, correct?
The second has a 98.2% pass on first try but still needs repair tools before final verification. The third gate is trickier because visual measurements are harder to validate automatically, about 4.9% retry rate.
So they measure how often these gates actually succeed overall?
While all 3 perform well, the third struggles more with multi-step reasoning tasks, like determining area from several measured inputs.
And accuracy testing. How do they verify that the Meiberger answers are correct?
Manual checks on 164 problems showed a median error of just 0.70%, which is solid for most tasks.
But what about those parabola area cases that hit only 93.97% accuracy?
Those outliers occur because multi-step derivations accumulate small errors at each stage, like chain reactions where one tiny mistake throws off everything downstream.
That makes sense. So they suggest checking intermediate results or using symbolic verification before combining answers to improve robustness.
Even with these weaknesses, their 1% accuracy threshold still delivers reliable outcomes because most solutions stay within 5% of exact values.
Okay, so we have reliability checks, error patterns, and improvement paths covered. What about the big picture? How does this all fit into real applications?
Think of it as identifying weak spots, then planning fixes. Even with multi-step challenges, they still hit their 1% benchmark because most answers remain close enough to be useful.
Sounds like practical progress rather than perfection.
And when we look at the results from 8 large language models tackling AnalyticGeo 7K benchmarks, performance varies dramatically by model.
Tell me about those numbers. What stands out?
Gemini 3 Flash using image input achieves 76.6% accuracy. GPT 5.2 and Claude Opus 4.5 follow closely at around 73 and 72% respectively.
But if we strip away the image component, even top models drop significantly to 23.2%?
Yes, showing that visual cues are essential for spatial reasoning tasks.
So the gap reveals something fundamental about how these models process geometry without visual input.
And they categorize goal types into 5 analytic geometry challenges, each with its own difficulty curve.
And the experimental setup varies too. Removing seeds, disabling quality gates, testing few-shot formalization. What does that tell us about performance drivers?
It shows cross-component verification and structured prompts matter immensely. Tweaking these elements exposes hidden weaknesses or strengths we might otherwise miss.
Interesting. And when they look at curve types versus goal types, is there a consistent pattern?
Not really. Every curve type proves harder than the last once visual aids are removed or text-only mode is enforced.
That reinforces why multimodal approaches matter for geometry problems.
Seeing shapes visually helps models grasp spatial intuition better than words alone can convey.
So if we're building tools around this, focusing on those tricky goal types first might give the biggest impact?
And that leads naturally into discussing formal verification combined with structured problem generation, potentially transforming how AI handles geometric reasoning altogether.
Sounds like a promising direction for advancing reliable spatial intelligence in machines. So when they talk about measuring from a diagram, they're not just crunching numbers, they're interpreting visual information like a painter reads colors.
They convert pixels on screen to real-world coordinates using pixel tocode, which is essential for anything the robot needs to interact with its environment.
I see why that matters. If you misread a line or curve, the robot could end up in the wrong spot entirely.
Right. That's why they flag unmeasurable points and decide whether to ignore them, interpolate, or capture better images.
So it's not just about getting exact answers. It's about knowing when something can't be measured reliably.
They treat curves as parametric equations and approximate intersections numerically when exact solutions aren't possible.
That makes sense. Curves in real life rarely match perfect mathematical lines, so approximations are necessary.
And they document everything clearly so others can adjust tolerances or resolutions depending on their needs.
So the system respects its own limits instead of pretending every point is perfectly defined.
This honesty prevents errors from snowballing when decisions depend on those measurements.
What about ambiguity in arcs or splines? Do they struggle with that too?
They handle it by treating curves as parametric equations and using numerical methods to find intersections.
So instead of forcing a straight line where there's curvature, the system accepts some uncertainty, but still delivers usable results.
And they let researchers tweak tolerances so the tool adapts to different applications.
That flexibility is powerful. It keeps the method practical without sacrificing rigor.
They document everything so others can replicate or extend their work confidently.
Now, when it comes to tools like Pixel Tocode, what's special about that function?
It maps screen pixels back into real-world coordinates using camera metadata, basically translating digital images into tangible data.
So if something is at 152,000 on the screen, we know exactly where it sits relative to the robot's surroundings.
And they use SDF renderer metadata for accurate conversions across different setups.
That sounds like a bridge between virtual and physical spaces, like turning a painting into measurements.
Every step is designed to keep the integrity of what's observed so downstream decisions stay reliable.
Speaking of integrity, why does rounding coordinates matter so much in their calculations?
Because tiny errors compound quickly. Small mistakes can lead to big misinterpretations later on.
So they pass every coordinate through compute functions without rounding until the very end.
The final number must stay exact because even minor deviations affect everything else downstream.
And what about avoiding analytical approximations? Why not simplify things theoretically first?
Because in robotics, theory alone isn't enough. You need numerical precision to ensure safe operation in real environments.
So it's all about preserving fidelity at every stage, instead of cutting corners.
They call it maintaining fidelity so the system behaves predictably when interacting with physical objects.
That mindset explains why they stress strict adherence to numerical methods over hand-wavy shortcuts.
It's about building trust in the system by being transparent and precise throughout.
Now, if someone wanted to visualize something using this framework, what would be the first step?
They'd render the diagram clearly on screen or with high resolution so everything is legible before conversion.
Then they feed that into pixel tocode to anchor spatial data before checking intersections.
If something's too far out of range, it gets labeled unmeasurable, so garbage data doesn't skew results.
So the process starts with clean visuals and ends with honest measurements.
Honesty to what can actually be seen keeps everything grounded in reality.
What about curved shapes that aren't straight lines? How does the system handle arcs or splines?
They treat curves as parametric equations and approximate intersections numerically when exact solutions are tricky.
So it's not magic, it's smart approximation with clear limits on accuracy.
And they document those limits so users know where approximations start and end.
That transparency builds confidence in the tool's reliability across applications.
It's all about balancing creativity with rigor so engineers can trust what comes out of it.
Speaking of balance, I'm curious, what happens if something feels too fussy or complicated for real-world use?
They acknowledge that strict rules sometimes clash with speed demands in fast-paced settings.
So they accept some approximation to gain efficiency when needed.
But still, the philosophy remains. Be meticulous about every measurement because small errors add up quickly.
That mindset explains why they're so careful even when things seem trivial.
Every digit matters when decisions affect safety or performance.
All right, Jamie, I think we've covered how this framework turns artistic intuition into precise engineering. Thanks for breaking it down.
My pleasure. It's fascinating how geometry and computation merge to make robots smarter and safer every day.
Thanks, Jamie. That clears up a ton.
Absolutely, those ground truth setups are crucial for bridging theory and practice in robotic geometry reasoning.
They reveal how symbolic models meet neural learning in real-world scenarios.
That's all we have for today. Thanks for listening, everyone.
See you next time.